Hello everyone. In this study, we focus on learning where and when to zoom using deep reinforcement learning. This is a joint work between Burak Uzkent and Stefano Ermon from Stanford University. Model compression has been extensively studied in the computer vision literature. Most of these studies focus on knowledge distillation, quantization, filter pruning, and adaptive layer dropping. Another simple way to achieve runtime efficiency is to downsample input images and run them through CNN. However, this results in reduced accuracy. Unlike model compression, there exists no adaptive method to adaptively sample images. Here we show the proposed framework called PatchDrop. We have the policy network that processes the low-resolution images and the classifier that uses the sampled image to classify images. Patch sampling policy is represented by pi1 and condition on low-resolution image XL and parameters theta p. It takes a binary set of actions for unique patches, where each output unit represents a unique patch, and in total we have capital P equal to 16 disjoint patches. And the second network classifies the sampled images using the classification policy, which is represented by action A2. Given class predictions, we reward or penalize the policy network. We now model the policy network and classifier. The patch sampling policy is the product of individual Bernoulli distributions, where each distribution represents a unique patch in the image space. Here, SOP represents the policy network output. On the other hand, reward function is a function of A1, A2, and Y, where Y represents the ground truth label for the image. It is a piecewise function that encourages dropping more number of patches only if the classifier successfully classifies the sampled image. At the end, our objective function encourages maximizing the product of action likelihood and expected reward value by learning the parameters of the policy network. Our training protocol consists of three sequential steps. In the first step, we pre-train the policy network while fixing the parameters of the classifier. In the second step, we jointly fine-tune the policy network and classifier network so that the classifier can adapt with respect to the mascot images. Finally, we propose an optional step which incorporates a low-resolution network to get a model ensemble that utilizes mascot images as well as low-resolution images. Now we conduct experiments on ImageNet and functional map of the world datasets. The functional map of the world dataset consists of very expensive high-resolution satellite images. At the top figure, we visualize the learned policies in the third row and fourth row. We can observe that the PatchDrop learns the sample from the critical patches of the high-resolution images. Overall, in both datasets, we can maintain the accuracy of the high-resolution CNN while using about 50% of the high-resolution images. The previous approach passes the whole mascot image through the classifier. Thus, as we process mascot patches, we cannot reduce the computational complexity. To address this problem, we propose adaptive patchwise inference that processes only sampled patches in parallel using a CNN with shared weights. Finally, we sum up the patch level predictions to compute image level predictions. We perform experiments on CFR10 where we can reduce the number of flops by about 50% while maintaining the accuracy of high-resolution CNN. We want to highlight that this approach does not change the underlying structure of the CNN, and we can visualize the learned policies in the bottom figure, in the third row. Another application of our framework is conditional hard positive generation to regularize CNNs. To achieve this, we simply mask out the most critical patches of the image to generate adversarial examples. We perform experiments on 4 different benchmarks, including ImageNet, and we outperform random masking out method, which is called cutout by large margin in all the benchmarks. Finally, you can access PyTorch implementation of PatchDrop in our GitHub repo. Please feel free to contact us for any questions and comments regarding our paper. Thank you very much for listening to our presentation.